So we'll finish up chapter 17 today and start into chapter 18. I hope to cover the first section of chapter 18, which would then mean we'll have a quiz on it tomorrow. We'll see how far into it we actually get, but that's going to be the intent. Okay, so the quiz will help kind of guide you through some of the solving for balancing equations. So I know you all love doing balancing of reactions in 151. We're going to do it again this semester too. So things we've covered. You've got your rules for entropy. Make sure you apply them accordingly. Start at rule number 1 and slowly work your way through it until you find a difference. The important relationships. I did go through and kind of highlight the sections independent of each other. Okay, so it might be easy enough to determine the ones in red, like kind of derive those. And those are either always spontaneous or always non-spontaneous. So it involves a little bit less thought with those, so maybe you can get away with not memorizing those.
When it says that low or high temperature, what's a low temperature? Like, what's the cutoff?
So as far as deciding, I don't think I have any space on this. We'll look at that in just a second here. The ones that I would highly recommend you memorize, because they're going to be a little bit trickier, is looking at how the Gibbs free energy, or whether it's spontaneous or not, changes with the temperature. So that's the high-low effect. Okay? You can memorize those, or you can just kind of derive them as you need them. It's kind of up to you. Okay? As far as deciding what is high and low, depends on what delta H is and what delta S is. So trying to figure that out, we can't just memorize what is high, what is low, because it depends on each reaction. So how would you determine it? Come on, there it goes. You could be given a question where you're given a delta H and a delta S, and it says at what temperature does this reaction become spontaneous? Okay, so anybody already memorize them? What's one that's temperature dependent? Delta H is what? What?
What, positive or negative?
Yeah.
Negative.
Delta S would need to be, isn't that always spontaneous? I want one that's not always spontaneous. Oops, I didn't erase it. S negative and H positive? Or no?
No,
Both negative. Okay. So let's pick some random numbers here. Let's do 298. Typically, when we look at units for delta H, it's usually in kilojoules or kilojoules per mole. If we look at delta S, because that energy contribution is usually a little bit less, and by a little bit, it's usually several orders of magnitude. Let's go ahead and make it, let's not make it extra confusing. Let's go with 100 joules per Kelvin. Okay? So we could be asked different pieces of information. Is it temperature dependent? Is it not? Okay, so determining temperature dependence, we could look at the sign and evaluate that yes, this does match one of those conditions. Our Gibbs free energy or our reaction will be spontaneous or non-spontaneous, dependent solely on the temperature. How do we figure out what that temperature is? Well, we would go back to our equation for Gibbs free energy. T delta S. Okay. So there's a few different schools of thought on this. I've noticed lots of students like the thought of I'm just going to plug in multiple choice answers until it works. Okay. That does work, but we can try and reason our way through this a little bit better. What we're looking at is where delta G transitions from being positive to negative. Okay. So where does that transition occur?
0.
At 0. So we can set this equation equal to 0. And now we could just plug in our numbers. Whoops. 298 kilojoules minus our temperature, which we don't know. We'll go through this with standard units. Whoops. Sorry, I'm used to writing moles. Okay, and we could go through and solve for temperature. What's the first easiest mistake to make?
Units.
our units aren't matched up appropriately. So we'd have to make sure we go through and do a unit conversion. And I heard the other common error, which is looking at signs. So when you go through to substitute, I would fully substitute in all of the individual signs first, and then go through and try and simplify. Okay, so to me, I would change this to now negative 298 kilojoules plus 100 joules per Kelvin times our temperature times our unit conversion. We've got 1,000 joules and 1 kilojoule. Okay. I'm going to shuffle some stuff around now. We get 298 kilojoules equals, make sure I did this right, 0.1 joules per Kelvin times our temperature. Whoops. What are the units on that side now? Kilojoules, we did do that. Shoot. Did do that unit conversion. Can now solve for our temperature. Temperature will equal 298 kilojoules divided by 0.1 kilojoules per Kelvin. We should get 29. No, other way. Yeah? Did I do that right? If we look at our units, our kilojoules cancel, and we'd get 1 divided by 1 over Kelvin, which is the same thing as okay. So where we see that transition is at 2,980 Kelvin. So that's a really high temperature. Where is it transitioning? Above that temperature, if we go to 2,981, are we spontaneous or non-spontaneous? I actually don't have it memorized. I'd go through and look at our numbers. We should be non-spontaneous, right? Did I do that right? You guys see how I got that? If we drop to 2,900, we're now at a lower temperature, which means if we go back in, I'll show you where I did that work. The negative delta S will cancel with our minus sign. If we use a lower temperature, that temperature value won't be enough to overcome our negative enthalpy, and we would get a negative delta G. We'd have a spontaneous reaction. Okay, does that kind of make sense? Yes.
So is 2980 like the line?
That's the line in the sand. Exactly right. So above that, we would be, I already forgot the math. Above that, we'd be non-spontaneous. Guess we can add that information down at the bottom. So a temperature greater than 298 Kelvin. Delta G is greater than 0. For a temperature less than 2,980, delta G is less than 0. Okay. So does that kind of make sense? Does that clarify your initial question? Okay. So what we're trying to go through and do is specify and apply each of those individual positions. Okay, yeah.
So a question would be, like you say, at equilibrium, what would the temperature be? And then that would be...
Or it would be, which of the following temperatures is delta G spontaneous?
Oh, so you find
Which of the following temperatures is the reaction non-spontaneous?
So did you plug that number back into where you put it?
Yes. Kind of, sort of. If we plug that number directly back in, what do we get for delta G? How did we get that number?
You plug that number into T?
Now, how did we get T? How did we get 298 or 2,980?
Yeah, you did the...
We assumed delta G was equal to 0. So if we directly plug that number back in, what are we going to get for delta G? 0. okay? Because that's how we solve for temperature. We solved for where delta G was equal to 0. If we're trying to find where it switches, when it becomes spontaneous or non-spontaneous, what we would do is add a degree to it or subtract a degree from it, because that will now give us a non-zero value. Okay? So we could say above this temperature, we're non-spontaneous. Below this temperature, we are spontaneous. If it's a list of temperatures, you would have to then plug one in and see if it's negative or not. Other questions? Hi. What button do I want to push? Hey, that worked. So where we ended last week was looking at how delta G can then be related back to the equilibrium constant or even the reaction coefficient. So we derived where this RT ln of Q or ln of K came from, which you either were interested in or not. Ultimately, what you need to be able to do is to apply this equation to different problems. Okay? So at equilibrium, our delta G is equal to 0 because both reactions are occurring at equal rates and nothing really progresses forward. Okay? So we get a delta G equal to 0. That means that Q is no longer Q because we're at equilibrium. Q becomes K. And we could sub that back into our equation, and we end up with this expression, that the delta G naught, or at standard states, is equal to RT ln of K. Okay? What is R? Which gas constant do we use? Why the 8.3145? We want our units to match. Delta G is a form of energy, which means the units on energy need to be joules or kilojoules. We have to use a gas constant that has those units in it. If you decide to switch it up to a different one, it is still technically a delta G, but we haven't converted the units appropriately over, and we technically get the wrong answer. Okay? Because we want some kind of energy term. What is capital T? It's our temperature in, why do we pick kelvins? It's always positive. Okay? We don't have to worry about sign changes on us. Natural log, so that's where we get our ln, and then K would be equilibrium constant. How do we solve for an equilibrium constant? Concentration of our products over the concentration of our reactants. Okay? So if we had our standard state Gibbs free energy, we could then go through and solve for our equilibrium constant. Okay? And that's where we could then switch things around, and we end up with this fun expression. We get those exponentials again. You'll notice that that does look very, very, very similar to one that we've seen already. That should look an awful lot like our Arrhenius expression, where we had lowercase k equals to our frequency factor times e to the negative activation energy over RT. Very, very similar as those two. Yes. Every formula you're always given. Okay? If you take a look at the equation sheet that is posted, I'm pretty sure all of these are already on there. Okay? I might put them on in varying extents because I do expect some kind of algebraic notation, derivation kind of stuff. So check with that equation sheet and make sure that you know which ones are there and how you can convert those around. Okay? Other questions? Okay. So now we can kind of go through and look at some ballpark estimations. What happens to the magnitude of K if our Gibbs free energy is less than 0? What happens to the reaction? Is it spontaneous or non-spontaneous? It's spontaneous. So what would we guess for K? If we've got a reaction that progresses forward, any ideas? If you've got a reaction that goes from reactants to products, we've got a spontaneous reaction, meaning we do form products. We might expect a larger value. Okay? So let's go through and see what happens. Okay? So what we'll do is take some guesses at it. We've got K as our products over reactants. Okay? So K is equal to some positive number. Why would K be equal to a positive number? What do we say delta G was? Delta G less than 0. What's its sign? Negative. So if we plug in a negative number right there, what do we get? Positive. K will equal E to some positive number. We don't know what it is. What does that mean K becomes? Greater than 1, which matches with our initial assessment. Okay. What side of the reaction is favored at equilibrium if delta G is greater than 0? Well, if delta G was less than 0, and we favored products, what do you think is going to happen when delta G is greater than 0? Probably going to favor reactants. How could we go through and determine this? Again, just plug in your assumptions. We're saying delta G greater than 0, which means the sign is positive. Delta G is positive, R is positive, our temperature is positive. We're looking at E to a negative number. I don't care what the number is, as long as it's a negative number. What's the result? We get K less than 1. Kind of makes sense? So what we can do is start to do some interpretations without having to do any calculator punch-in whatsoever. Why is that really important? Well, as we've seen in previous sections, calculator punching in appears to be incredibly difficult. Okay? It's really, really easy to make that simple mistake, and you get the wrong answer. If you forgot the minus sign, now all of a sudden, you're going from it being a spontaneous reaction to a non-spontaneous reaction. Okay? So if you don't have a way to check your answer quickly, to verify that what you punched into the calculator was actually what you were supposed to do, you will get the wrong answer. Okay? This goes back to some of the reasons behind why we still teach arithmetic. Okay? It's a common thing for engineers to go, why do I need to learn how to add, subtract, multiply, divide? It's completely silly. I've got a calculator that can do it for me. Absolutely right. We have computers and calculators that can do all of this mathematics for us. That's fantastic. Who puts the information into the calculator? We do. If we screw it up, what happens? In the case of an engineer, the building falls down. In the case of a doctor, okay, we kill a patient. Okay? You have to have some understanding of what's happening behind the scenes before you can apply technology. Technology is a tool, it is not a crutch. Okay? So, let's go through an example problem. I thought this was actually kind of an interesting one from your homework. Both Connect and Sapling have roughly equivalent versions of this exact problem. Okay? So one of the reasons why I liked it, because I noticed this was a lot of problem, or this caused a lot of issues for students on previous exams, is being able to convert what's said in English into chemical equations. Okay, to try and come up with some information to apply it. Okay? So we're given some reaction with a delta G naught, and you'll notice that if we look at that Gibbs free energy, what sign is it? Positive. Does that reaction occur? No. Why would we want to run this reaction? What does M stand for? Metal. Typically, your metals are not found in their pure form. They're found in some kind of oxidized state. Why oxidized? Because oxygen is extremely reactive. So when we've got oxygen in our atmosphere, that reacts with our metals, turns them into these metal oxides, okay, or other compounds. So why is this reaction of particular importance? Well, if I want to get the pure metal, I have to get rid of the oxygen. Okay, so we could go through and say, okay, let's look at just that reaction. How can I convert the metal oxide over to my pure metal and oxygen gas? Okay, we could try and heat it up, melt it, burn it, do whatever we want. We look at the Gibbs free energy, what do we see? It's positive, which means it's non-spontaneous, which means what happens if we try and heat it up, turn it on its head, pressurize it? Absolutely nothing. The reaction will never occur. So what we've got to do is couple it to something else in the hope that in the process of that extra step, that extra coupling, we can now convert that process or that Gibbs free energy into a negative value. With it being a negative value, what can we do? It's now a spontaneous reaction. We could actually produce products out of that. Okay? So the common coupling process is looking at the conversion of graphite to carbon dioxide. We're then given some extra information. Number one, we're told that the reaction becomes spontaneous when we do this coupling, which is nice. What does that mean the Gibbs free energy will be? Negative, assuming I did the math right. Okay. And then we're given some thermodynamic data for it. The next part of it, or what the question is actually asking for, is what is the equilibrium constant for the coupled reaction at standard conditions? Okay. That gets a little bit trickier. How do we solve for an equilibrium constant? What was that? We've got the equation K equals e to the negative delta G over RT, right? In fact, I need to fix that a little bit, delta G naught. Okay, so that's useful. We could go through and solve. I'm given a delta G naught, plug it in, we get an answer, right? Is that the right answer? No, why not? Okay, we're looking for the delta G for the coupled reaction. Yes, we're given a delta G. Is that for a coupled reaction? No, that is only given for the metal oxide conversion. So what we have to do is determine what the delta G is for the coupled reaction, which means we're going to have to go through a couple other steps. We need to figure out first off what that coupled reaction looks like. Okay? So what we're doing is going to add two reactions together. We're going to convert our metal oxide across at the same time that we do this other conversion. So what does that other conversion look like? We don't want to look at an equation necessarily yet. We want to balance reaction first. We're looking at carbon plus oxygen going to CO2. Why do we know we have oxygen in there? The problem didn't say anything about oxygen. It just says graphite to carbon dioxide. You have to have the oxygen there. Why? Please explain to me how we can get carbon to carbon dioxide without oxygen. Okay? So some stuff is naturally implied when they go through and do these conversions. You need to make sure you're aware of that. Okay? So we could then go through and add these two reactions up. When we add our reactions, you should notice that we'll get, I wonder if I left myself enough space. Our carbon goes to metal and CO2. What happened to the oxygen? Canceled out because it's on opposite sides of that equation. Okay? There's the coupled reaction. To use my equation, K equals E to all that stuff, what do I need? I need the delta G for this reaction. What is the delta G for this reaction? Okay, we've got a couple ways we could go through and solve. We could go through and look at the delta G of formation for each of the species within our balanced reaction. Okay, except what's the problem with looking at our coupled reaction? What's going to be the delta G of formation of some metal oxide? We don't know that because we don't know what the metal oxide is. Okay? So that prevents us from going to thermodynamic table to figure that out. So what we'll do is instead go to what Aaron was suggesting. We need to figure out the delta G for our carbon to carbon dioxide conversion. We can use a Hess's law relationship and we can then add our delta G's. Okay? So we can add the delta G of the individual reactions to give us the delta G for the overall reaction. Okay, so now what we could do is look up the delta G of formation of carbon dioxide. We're given that. What's the delta G of formation of carbon? Graphite. 0. How do you know it's 0? Nope. Pure is closer. But we can still have a pure solid that has a delta G of formation. Anything in its elemental state has a delta G of 0 for its formation. Why? Because it's in its elemental state. That's what we've decided is its standard state. So anything in its elemental state has a Gibbs free energy of formation equal to 0, because that's where it's supposed to be. Okay? So we could go through and look up the formation for CO2, and that would be our Gibbs free energy, except we're going to assume you don't have a textbook. So by giving you that information. No. So what do we have to do then? Do we know the delta G is related to anything? We looked at one option, our Hess's law format, adding our delta G's of formation. We don't have that information. What's the other format? Okay. Are we given a temperature? Yes. Are we given a delta H? Yes. Are we given a delta S? Yes. We can then go through and solve for the delta G naught for our carbon to carbon dioxide conversion. Once we've got that number, what can we do? Our delta G for our reaction will equal the delta G naught of our metal plus the delta G naught for our carbon dioxide. Once we have the delta G for the reaction, what can we then do? Go all the way back to where we initially said to start with, plug it in, and solve. I did not solve this, so I'm not going to attempt to punch in numbers. Questions about formatting that? Is that a no? No questions? The idea is to try and convert as much information out of the question as possible and get it into a format that you can manipulate and use. Don't automatically just pick an equation and start jamming things in that look similar. You have to make sure you know what they're applying to. Yeah.
So the delta G naught equation at the top, right? That you use that for the delta G naught CO2?
Yes. Yeah, I guess the question was a bit questionable on what those values applied to. Those were supposed to, where'd you go? Those were supposed to be the CO2. Okay. Questions about that? Yes.
On the equations sheet, there's like a delta G just like without the degree sign, and like, so do you just like manipulate it to make it look like that?
Which, this one?
Yeah, that one.
So there's a couple formats for your delta G that you might see floating around. We've got the one format, whoops, at the top, our standard delta Gs. Kind of color this so we can see different formats of this. You might also see a delta G equals delta H minus T delta S. What's the difference between these two equations? They aren't exactly the same.
One's STP or standard.
One's at your standard conditions, one's not. Okay? The equation still holds true regardless. Okay? So it's just a question of which conditions you're looking at. One of the other formats that you might see is you're asked to solve for a temperature for a delta G for a reaction at non-standard temperatures. Okay? In that case, we cannot use the top equation because delta G is at standard conditions. So that equation doesn't quite make sense. Delta G down here is not at standard conditions, so we could get away with changing our temperature. Okay, we could use this format. But then what's the next issue? How would we know what our delta H and our delta S are? Are those temperature dependent? So let's say I want to know the Gibbs free energy for the conversion of graphite to carbon dioxide at 400 Kelvin. I'll erase all that now. What is delta G for our CO2? Sorry, that's an at sign. At 400 Kelvin. We're actually given all the information we need to solve this one. Well, it's going to be delta G. I'm not going to rewrite that. Maybe I'll kind of rewrite it. Delta G is equal to our delta H at 400 degrees Kelvin times our temperature, which will be 400 Kelvin. I'm cool with that. Times our delta S. What values do we plug in for our delta H and our delta S? So this is an interesting question. What are you saying?
Delta S in joules, we convert it to kilojoules first.
So we can convert that over to kilojoules, but that's delta S at standard conditions, not delta S at 400 kelvins. See the kind of dilemma on that one? We have to make an assumption to solve this. What's that assumption? Our delta H at standard conditions does not change when we change the temperature, or rather does not change enough to make us concerned about how it changes our delta H. Shadow, that delta H. So what does that mean we can plug into our equation? Our delta H at our standard conditions, and we would plug in 393 kilojoules, and for the other one, it's positive 0.214 kilojoules per mole. Kelvin, sorry. Okay. It's a really simple assumption. I don't think the textbook actually clearly states it. So thank you for bringing that up, because I did want to address that. Just didn't know when to address it. So if we're asking to solve for Gibbs free energy at a non-standard temperature, we would technically need to know the enthalpies and the entropies at that non-standard temperature. Okay? That's how we can use that equation. Okay? So to be able to simplify this and actually allow you to solve for it, what we end up saying is that the enthalpy and the entropy are not temperature dependent enough that they will change substantially from our standard states, and we can plug those numbers directly into the equation. Okay? We can now go through and solve for our delta G at 400 kelvins. Okay? So that was a nice circular way to go back to your question. What's the difference between those equations? There isn't. Okay? Other questions on this? Okay. So some important definitions. I'm not going to talk through them, but you should remember these. Where it gets tricky is a lot of these definitions overlap with each other. You see similarities between them. Okay? So make sure that you keep them separate, independent terms. When we look at enthalpy, you know you're looking at exothermic, endothermic, wind's positive, wind's negative. Okay? So make sure you apply those terms carefully and independent of each other. Okay? Kind of back to that spontaneous versus non-spontaneous. Okay, we did address this. Spontaneous in most people's minds means instant. When we look at thermodynamics, spontaneous says nothing about time. It only says that the reaction will occur. If you just downloaded the slides, you won't have this on there. It's an older slide. I just copied and pasted. So when we're looking at spontaneous again, okay, it's just saying that the reaction can occur, which isn't the easiest definition to identify. That's where, when we talked about it, we went back and looked at non-spontaneous. And our definition of non-spontaneous is that it never occurs. Okay, it's something that cannot possibly occur at those conditions, which means spontaneous, being the inverse of that, just means that it can occur. There's no time assumption with it. It just means that it is a process that will occur given enough time. Okay? The classic example of this is looking at human combustion. If we look at the thermodynamics of us turning into oxygen or CO2 and water, if we look at us as a reactant, kind of unpleasant, and we look at the product of us as CO2 plus water, that reaction is very, very exothermic. In fact, let's be really dramatic. Might as well. That's an eraser. Really, really, really exothermic. There's a huge difference between our reactant and our product. Okay? Why do we not, or why do we exist at all? Well, we exist because, thankfully, there's a very high activation barrier, which I'm going to draw off the scale here. That activation barrier prevents us from converting into CO2 and water. Okay? That activation barrier is not described by thermodynamics. We have to go back to kinetics to evaluate that. Okay? Which takes us back to, well, almost back to that. Looking at the relationship between our thermodynamics and kinetics, what do they mean? How do they apply? Why are we looking at them? Comes back to these energy diagrams. Okay? So what we're evaluating when we go through and look at an individual energy diagram, thermodynamics describes the relationship between our reactant and product energy. It does not describe how we get to the product from our reactants, or vice versa. To figure that out, we would have to shift into kinetics, and that's describing that upper bound. Okay? Our reactant energy to our transition state, or for the reverse reaction, our product energy to our transition state. Okay? The relationship between all of those sums together all reactions. Okay, looking at each of these individual barriers to a reaction occurring and each of the things favoring a reaction actually occurring. Okay? So this is kind of the summary, if you will, of looking at chapter 13 and chapter 17. Okay, putting it all together. Questions about anything in that chapter? Okay. That puts us into chapter 18, which is our electrochemistry chapter. I've put up some textbook questions. So as far as the textbook questions go, that first line should get you practice guaranteed. Everything in that line should be on the exam. The second line, that might show up on the exam, but it kind of just depends how far we get this week. And then those very last two questions, which oddly enough, Sapling has no questions on that material, and Connect has 50 billion questions on that material. That will show up on your final. Okay? If you flip through the slideshow, somewhere slide 60-ish, it tells you what sections we're going to skip or likely not see. I just forgot to put that up here. Okay? So to go ahead and start off, what we're going to do is actually go backwards instead of going forwards. So the hope is we can go backwards so that we can go 5 steps forwards. That makes it nice, right? So we can slow things down a little bit. What I would recommend you do is review chapter 4, section 4, and those page references are correct within the Chang textbook. What those references are looking at is redox reactions. How to determine oxidation states. What is an oxidation state? Some sort of simple balancing, though we're going to look at much more complex versions of it. Okay? You have to be adept at this material to be able to do anything in this chapter. Okay? If you have any problems with determining oxidation states or any of the rules that are up here, you need to be practicing it daily because you got the exam next Monday. Or asking questions about it to slow me down a little bit. Okay? All this material is stuff that I expect you to already know. Okay? So, let's go through and take a look at some examples. One of the things that I like to kind of address is the difference between charge and oxidation state. Okay? They are, believe it or not, different things. We can have a charge on a molecule that means nothing about the oxidation state. So charge applies to molecules, oxidation states apply to atoms. Okay? In some cases, particularly simple structures, the charge and the oxidation state are the same thing. Okay? And that's where a lot of that confusion can come in. So if we go ahead and take a look at some of the examples for charge. Where do we find the charge written? Upper right-hand corner of everything. Any molecule ever drawn in any chemistry class will show the charge in the upper right-hand corner. Yes, it gets formatted slightly differently. I apparently format it differently than anybody else I've seen, but tough. Okay? So what's the charge for that first atom? 0. How do you know it's 0? Nothing written there. Okay? For the next one, +2. Good thing I timed that to sequence perfectly. Okay, and we've got all of those charges written in the upper corner. The next part of it is looking at the oxidation state. So to determine the oxidation state, that's where we'd end up using this formula. Unfortunately, it jumped lines. We look at the number of an element within an individual formula times its oxidation state, plus the number of the next element times its oxidation state. And we add all of those terms up, and what we get is the charge. So let's take a look at our first molecule. Okay, how many of those elements are there? 1. And its oxidation state. Okay, since we're trying to determine that, we technically don't know it yet. So if we're going to solve this out, we've got 1 times the oxidation state equals the charge. The charge on that molecule was 0. What is the oxidation state? 0 divided by 1 is 0. Look at that. The oxidation state and the charge are the same. We move to the next one. How many elements do we have of that? We've got 1 times its oxidation state. Technically, we don't know it. Equals our charge, which is, how do we know it's +2? Upper right-hand corner. What is the oxidation state of copper in that? +2. Okay? So in these first two cases, the oxidation state and the charge ended up being the same. What happens when we move to the next one? How many nitrogens are there? What's its oxidation state? Plus. How many oxygens are there? How many oxygens are there? 3 times the oxidation state. What's the oxidation state? Okay. Based on our memorization skills, we would remember from that previous slide that oxygen will always have a -2 charge, so we can immediately sub that in here if you would like to. If you don't, you have to put in some other variable, okay, a y if you want. Then we're stuck because we've got one equation and no way to solve for the 2 unknowns. Okay, so you have to have the oxidation state memorized. What does this then equal? The charge, which is our -1. We can now solve for x, and we get x equal to +5. Okay? Some of the oxidation determinations are easier than others. Ultimately, this equation will never fail. I hope. Okay? We could go through and do it with the last one. But I'm just going to stepwise because I think I did it for the last one. And we should see that sulfur comes out as a +6 and the oxygen comes out again as a -2. Okay? Is oxygen always -2? No, except when it's a peroxide. Okay? So you might see that show up in your textbook questions or in the homework online. I don't think I will ever test you on that specifically because it's just going to mess with your head even more than we need to. Okay? Questions about charge and oxidation state? Good. Okay? So we could go through and work another problem. So how about you guys go through and start this one and determine the oxidation states for all elements within this.